This is Miss Young, and it is just me tonight, and I'm on my iPad, so you're actually not getting any video. And I'm going to quickly talk through 5-8 sampling distributions for differences in sample means. And when we look at this section, it is quite similar to the last two sections. And so the only real difference here is instead of difference in proportions, now we're talking about difference in means, and we're going to switch formulas a little bit. So you can see here in our essential knowledge that we're still needing mean and standard deviation, always coming back to mean and standard deviation. In order to find the mean in the difference of means, you just subtract the means. It's not groundbreaking. And then in order to find the standard deviation, you do the standard deviation squared divided by the sample size plus the second standard deviation squared divided by that, the sample size, and then you take the square root of all of that, okay? 10% condition is still in effect here, and you know that's the one that says, hey, we can use this standard deviation formula if our sample is not more than 10% of the population size, and then also we want to make sure that our population is either normal or our sampling is greater than or equal to 30. Okay, so we're coming back to the 30 thing, and we want to make sure that our sample size is larger than 30, greater than or equal to 30. Okay, and of course we want to make sure that we are staying true to our units and context and all of that stuff. Okay. So our first example here says a population, or population 1 has a mean of 20 and a variance of 100. Population 2 has a mean of 15 and a variance of 64. You sample 20 scores from population 1 and 16 scores from population 2. What is the mean of the sampling distribution of the difference in means from population 1 minus population 2? Okay, so this is really simple. I need an annotating tool, so I'm about to flip over here, and I'm going to pause this until I figure out how to annotate. Okay, so all we have to do in terms of finding the mean in a problem like this is to actually just subtract. Okay, so it says we have a mean of 20 for population 1 and a mean of 15 for population 2. Okay, so if I'm looking at this formula right here, then mu of x bar sub 1 is 20, and mu of x bar sub 2 is 15. And so if I want mu of x bar sub 1 minus x bar sub 2, then I'm literally just subtracting 20 minus 15 and getting 5. Okay, and the math here for the standard deviation is just follow the formula right here. Okay, so we've defined our variance, but we haven't defined our standard deviation. But in case you have forgotten, standard deviation squared is the variance. Okay, so I don't need to take the square root of this just to square it again, if that makes sense. So if I want to find standard deviation of x bar 1 minus x bar 2, it's going to be the square root of that variance from population 1, which is 100, over that size. And so population 1 is 16, okay, plus the information from population 2. So it has a variance of 64. Now, if it gives you standard deviation, you're going to have to square it to get that variance value. Okay, I messed up here, you sampled 20 scores from population 1, so that should be 20, and 16 scores from population 2. My fault. Okay, and then you can just plug this straight into a calculator. Obviously, I can't just take this individual square roots here, and I can't add because they don't have a common denominator. And so I'm looking at 64/16, which is 4, and 120th, which is 5. And so that's the square root of 9, meaning my standard deviation for the difference is 3. Okay, so if that makes sense. All right, let me pop back over here to my slides. And it says the mean height of a 15-year-old boy is 175 centimeters, and the variance is 64. For girls, the mean is 165 and the variance is 64. If 8 boys and 8 girls were sampled, what is the probability that the mean height of the sample of boys would be at least 6 centimeters higher than the mean height of 6 girls? Okay, so I'm going to head over here to Zoom, pause this, get a picture so I can write. Okay, I have a picture now. And I'm looking at means here. So I've got my first mean height, unless we're going to just edit. My first mean height is this is X bar 1 for 15-year-old boys is 175 centimeters. And the standard deviation for X bar 1, the variance is 64. So remember, variance is just standard deviation squared. For girls, the mean is 165 centimeters and the variance is 64. Okay, 8 boys and 8 girls are sampled, so we're going to say not n, but we're going to say n sub 1 is 8, and we're going to say n sub 2 is 8. Okay, so now I've kind of collected all the information that they've given, and they want to know what's the probability, okay, which means I'm going to need like Normalcdf here, okay, in order to be able to do this. And so, just thinking about this, if I want to think about Normalcdf, and right now you should be yelling at me and telling me that I don't have a big enough sample, and you're right. Height is generally normally distributed, but you would really want to be told that. Okay, so I'm kind of cheating a little bit with this problem. So if I think about this, I'm wanting to put something on the normal curve here, and I'm wanting to compare when the boys would be 6 centimeters higher. Okay, so I'm going to subtract them. If they're the same height, it would be 0, right? And so boys higher than 6 means that if I subtract the boy minus the girl, I get 6. So I'm looking at mean of X bar sub 1 minus the mean of X bar sub 2, which is the boys minus the girls here. Okay, so this is like boys minus girls. So I get 175 minus 64, and I end up with minus 175 minus 165, and I get 10. Sorry, 175 minus 165. Then I want to find the standard deviation. So I'm going to that same formula that we looked at just a second ago. So I'm looking at just the subtraction of the 2. Right. So I've got variance over n plus variance over n, which is going to give me, what is that? 128 over 8. 128 over 8 is 16. And so I have the square root of 16, which is 4. Okay. So on my normal curve, I have a mean of 10 and a standard deviation of 4. So I can count 4 up and then 4 more up. And then what do we have? 4 less and 4 less. And the question that's being asked here is 6 higher, right? So here's 6, and I want 6 or more, okay? So here's kind of what I'm looking at here. And so I'm going to do normal CDF. And my lower bound is going to be 6, and my upper bound is going to be 99999. And remember, you defining these. You have to define these for the AP test. So I've got 6 to 99999 with a standard deviation here, or a mean of the x bars subtracted is 10. And then a standard deviation that is, let's see here, standard deviation of x bar minus x bar is, what do we find? 4. Okay, so I'm going to put this in my calculator, which I don't actually have pulled up because I'm so irresponsible. And what it's going to do is it's going to give me a nice, pretty number. Okay, now, I looking at this, guys, I don't really have to go to the calculator, because if I know my empirical rules, then I really can just add my empirical values. Okay, so thinking about what that means in this case, well, here is my 50%, right? One standard deviation to the left is 34%. So I can say the probability of the boys being more than 6 centimeters taller than the girls is about 84%. About 84% of the boys are going to be at least 6 centimeters taller than the girls. Okay. All right. Moving on. We're hitting done. Moving to the next one. Says the mean time that it takes to complete a task is 727 milliseconds for 3rd graders and 532 milliseconds for 5th graders. The variances are 12,000 and 10,000. Okay, so my first mean here is 727 milliseconds, and my second mean is 532 milliseconds. And then we're given variance, so pay attention to what you're given. So my first variance is 12,000 milliseconds, and my second variance is 10,000 milliseconds. And it says the times are normally distributed. This is so important for them to tell us this, because while heights are commonly normally distributed, and we can just assume that, we can't just assume that with most things. So we're going to randomly sample 12 third graders, which makes my, keep doing M and I don't mean to. My N sub 1 is 12, and my N sub 2 is 14. Again, those numbers aren't big enough, but they told us this time that we're normally distributed, so we can just assume it. So again, we're going to need a normal curve, because it says what is the probability. So that tells me go to the normal curve. Okay, and so this time we're looking to see what's the probability that the 5th graders the mean time of the 3rd graders exceed the mean time of the 5th graders by 150 milliseconds or more. Okay, and so I need a mean, so I'm just going to subtract again. I'm going to have 727 minus 532. So I'm going to go 727 minus 532, and that's going to give me 195 milliseconds for my mean. Okay, now I need a standard deviation. I'm going to my big formula, and I'm going to do variance over n. So 12,000 over 12 plus 10,000 over 14. And 12,000 over 12 is 1,000. So that's nice and easy. 10,000, 1, 2, 3, divided by 14 is not pretty. Okay. And I can add these two and then take the square root. If I can make my phone do what I want it to do. So that's going to give me about 41.4. Okay. So if I go up and down 2 standard deviations, I would add 195 to the standard deviation. It's going to give me 236. Add it again. Remember, I'm rough estimating here to get an idea of what this is looking like. And remember, this is my mean. Okay. So now I'm going to go to the left. So that's going to be 195 minus 41.4. Being lazy here and just rounding up to whole numbers. And I'm going to subtract one more time, 41.4. And that's going to give me 112. Okay. And we're looking for that place where the third graders exceed by 150 or more, 150 or more. Okay. So 150, that's going to be really close to here. And so I'm looking at or more is here. And I can't just use my empirical rule this time because I'm not on a perfect value or like one exact standard deviation or something like that. And so I absolutely have to use my normal calculator this time. Okay, so my lower bound is going to be 150, and my upper bound is going to be all the 9s. And the mean of the differences is 195, and the standard deviation of the differences is 41.4. So just defining it, and then saying, okay, I'm using my normal CDF to figure this out. Right? I'm gonna move that, and then 195, and then 41.4. And let's see here, let me enter it in. I said 150, upper bound is a whole bunch of 9s, mean is 195, and standard deviation is 41.4, and calculate. And I end up with an area up very close to the same as the last one, which we kind of would expect because this picture looks very similar to the last one. And so I don't have a lot of room here, but basically what happens is the probability of the third graders exceeding by more than 150 milliseconds is about 86.15%. Okay. So that's it. That's what you're going to be working on. Pretty straightforward because we've done this so much now. So I hope that was really, really helpful. You have a couple of Khan Academies, mean and standard deviation, and then shape. So just kind of work your way through it. Good luck. That is the last video for this semester. So I will see you on the flip side of the winter holiday. Bye.